Dear students, today's topic is the energy stored in a capacitor. You know what is a capacitor? A capacitor, it is a device which is used to store electrical energy by storing electric charge. How charge is stored in a capacitor? A capacitor consists of normally two conductors, which is one is positively charged and other is negatively charged. How it is charged? It is connected to the terminals of the battery. The process of charging or to work done to charge the capacitor is stored as its electrical energy or potential energy. Then how to charge the capacitor? Now consider a capacitor having capacitance C, and it will have two conductors 1 and 2, and to charge the capacitor we have to transfer the charges, suppose bit by bit, from plate 2 to plate 1, because at any instant there will be a point of time where the plate 1 or the conductor 1 is at higher potential than the conductor 2. So when you transfer the charge from conductor 2 to conductor 1, some work is to be done against the potential difference. Because you know what is potential difference. Potential difference is the work done per unit charge. Work done to transfer unit charge is the potential difference. So as there will be some potential difference, because an electric field will be present at any instant, when charge, suppose your plus Q there minus Q, electric field is there. If you want to transfer the charge, some work is to be done. That work done is stored as its electrical energy. Now what is the energy stored? So now consider capacitor whose capacitance is C, and we are transferring the charges bit by bit from conductor 2 to conductor 1. So for that, to calculate the total amount of work done to transfer the charge Q, first you will take a very small charge, that is dq dash, to transfer from conductor 2 to conductor 1. Then now consider an intermediate situation in which conductor 1 has a charge plus q dash, conductor 2 has a charge minus q dash. If here charge is plus q dash, here charge is minus q dash, what is the potential difference? The potential difference V is equal to q dash by C, because you know C is equal to q by V, so V is equal to q dash by C, and V is the work done to transfer unit charge. Then what is the work done to charge the transfer dq dash from plate 2 or conductor 2 to conductor 1? That work done is dW is equal to V dq dash, because V is the work done to transfer unit charge. To transfer the charge dq dash, work done is V into dq dash, and V is q dash by C into dq dash. Then what is the total work done? The total work done to transfer charge Q is given by, how to get this one? We have to integrate it. The W is equal to integration of dW, that is integration of q dash by C dq dash. What are the limit points? 0 to q, minimum is 0, maximum is q, and after integration what you will get? 1 by C will come outside, q dash square by 2, and the limit points are 0 to q. So finally this will be q square by 2c. As I told you earlier, this work done is stored as its electrical energy. Then what is the expression for energy stored in a capacitor? U is equal to q square by 2c. And also using this one, you can get a number of expressions for energy stored. And again, when you know V is equal to q dash by C, or q is equal to C into V, so now for q we can write CV square by 2c. Now you are getting another expression, that is u is equal to half CV square. When capacitance is given, V is given, you can calculate the energy using this formula. And if C is given, charge is given, you can apply this formula. Once again, you will get another formula for energy stored. U is equal to, you see, Q square by 2C is the energy stored. For C, what you can put? Q square is equal to 2 into Q by V, or that is equal to half Q V. Now you have got three expressions for energy stored in a capacitor. One is Q square by 2C, second one is half CV square, another is half QV. If Q is given, V is given, you can apply this formula to get the energy stored in a capacitor. So this is how you can calculate what is the energy stored in a capacitor. Now we have derived the expression for the energy stored in a capacitor. And you know, capacitor stores energy by storing electric charge. Now it consists of two conductors or two plates having charges plus Q and minus Q. And in the space, suppose for example, you take a parallel bed capacitor, it consists of two plates. So in between the two plates, there exists an electric field. That means in that space, energy is stored. And whatever energy stored per unit volume of that space is called energy density. You know what is density? The density is the mass per unit volume. Similarly, energy density is the energy stored per unit volume in that space in between the two conductors or two plates of the parallel bed capacitor. We have taken one example here, parallel bed capacitor, and let us find out the expression for the energy density. So now, if here the charge is Q and the surface area is A, we can write sigma is equal to Q by A. What is sigma? Sigma is the surface density of charge. This plate surface density is plus sigma. This plate surface density is minus sigma. Then what is the electric field that exists in between the two plates? If you remember, when we have derived the expression for the energy stored in a parallel bed capacitor, the electric field is equal to sigma by epsilon naught. That is the field that exists in between the two plates of the parallel bed capacitor. E is equal to sigma by epsilon naught. We have derived this one. We have taken the two plates. We have used the formula for an infinite plane sheet of charge. For each plate, sigma by 2 epsilon naught. So when as they are acting along the same direction, we have added and we have got the expression sigma by epsilon naught. So sigma is equal to epsilon naught E. Then what is Q? From this formula, Q is equal to sigma into A, and sigma is epsilon naught E into A. And the expression for the energy stored in a capacitor, we have taken an example parallel bed capacitor. U is equal to Q square by 2C, and Q is epsilon naught E A square divided by 2C. And you know, the capacitance of a parallel bed capacitor, the formula is C is equal to epsilon naught A divided by B, where A is the area of each plate, D is the distance between the two plates. So epsilon naught E A by whole square by 2C, just put the value of C, epsilon naught square E square A square by 2 epsilon naught A divided by D. Finally, what will you get? U is equal to half epsilon naught E square, one epsilon cancel out, A into D. This is the expression for energy stored. Then what is the energy density? Energy density U is equal to total energy stored divided by volume of the space between the two plates. If area of each plate is A and distance is D, the volume is A into D. So energy stored per unit volume equal to A into D. So that means U is equal to half epsilon naught E square. So this is the expression for energy density of an electric field. Now it depends upon the medium between the two plates epsilon naught and the value of electric field that exists in between the two plates of the two conductors. Although we have derived this expression for a parallel plate capacitor, this is equally applicable for different type of charge distribution also. Now, suppose a number of capacitors are connected in series or parallel. Then what is the expression for energy stored? So now, if a number of capacitors are connected in series, you know in series combination what remains constant? Q is equal to constant. If Q is constant and total charge remains constant, and what is the expression for capacitors in series combination? So 1 by C is equal to 1 by C1 plus 1 by C2 and so on, 1 by Cn. And energy stored in the combination, that is Q square by 2C. Now just multiply Q square by 2 in every expression, every term. Q square by 2C1 plus Q square by 2C2 and so on, Q square by 2Cn. That means the energy stored in series combination equal to U1 plus U2, and that means the total energy stored in series combination equal to sum of the energy stored in the individual capacitors. Then what happens in parallel combination? You know in parallel combination V is constant, and if V constant, then what expression you will apply? So the expression for energy stored, if V is constant, you can apply the formula half Cv square. And you know Cp means capacitance in parallel combination, that is equal to C1 plus C2 up to Cn. And now multiply half of V square to every expression. So half Cp into V square, half C1 V square plus half C2 V square and so on, half Cn V square. That means once again, as before, U parallel is equal to U1 plus U2 up to U1. That means the total energy stored in parallel combination equal to sum of the energy stored in the individual capacitors. Whether it is in series or in parallel, both cases the energy is additive. Now let us solve a question based on energy stored in a capacitor. This is a question in the CBSE 2017. Suppose two capacitors 12 picofarad each are connected in series to a battery of potential difference 50 volt. Now what is the energy stored? To calculate the energy stored in this combination, let us find first what is the capacitance of the series combination. So you know the formula 1 by C is equal to 1 by C1 plus 1 by C2. CS equal to C1, C2 by C1 plus C2, just put the values 12 into 12 by 12 plus 12, finally we will get 6 picofarad. That is the capacitance of the combination. Now what is the energy stored? U is equal to half CV square, V is 50. After putting the values, you will get 7.5 into 10 to the minus 9 joule. So this is how you can calculate energy stored in this combination. Now suppose the same two capacitors are connected in parallel. Then what is the energy stored? In that case, what you will do? You will find the energy stored capacitance of the parallel combination. Cp is equal to 12 plus 12, that is equal to 24 picofarad. And now what is the energy stored? U is equal to half Cp into V square, and Cp is 24 into 10 to the power minus 12, it is picofarad, into V is 50 into 50. Half is there, so that is equal to, cancel it, 12 into 5 is 60, into 5 300. So finally what you will get? 3 into 10 to the power minus 8 joule. This is the energy stored when they are connected in parallel. In parallel they are connected, energy is different. In series they are connected, energy is different. This way you can solve small numericals. Now suppose two conductors, conductor A and B having charges Q1 and Q2, they are connected by a connecting wire, a conducting wire. Then what will happen? Then what is the expression for common potential? Is there any loss of energy or increase in energy? That we will find here. Now, suppose two conductors A and B, a charge of A is Q1, charge of B is Q2, and they are connected by a very thin conducting wire, and these two are two insulated conductors. Then what will happen? If here charge is Q1, here charge is Q2, then there is a flow of charge. When they are connected by a conducting wire, then there will be a flow of charge. The flow of charge will be, the positive charges will flow from higher potential to lower potential till the potential of both the conductors will remain same. Now suppose here potential is V1, here potential is V2, and the charges are flowing from higher potential to lower potential. Then capacitance, suppose for this one the capacitance C1, for this conductor is C2. This conductor has capacitance C2. Now, then what is the total charge of the system? The total charge of the system Q is equal to Q1 plus Q2, and Q1 is equal to C1 Q1, and Q2 is equal to C2 V2. By definition, by formula, Q1 is C1 V1, Q2 is equal to C2 V2. And what is the total capacitance of the system? As you say, these two insulated conductors are very large distance apart, and the capacitance of this connecting wire is very less. Then you can say the total capacitance of the system C is equal to C1 plus C2. Now the total charge Q is equal to Q1 plus Q2, that is C1 V1 plus C2 V2, and capacitance is equal to C1 plus C2. Then what is the expression for common potential? This V is equal to common potential. When charges are redistributed and the potential remains same, there is no flow of charge, then V is equal to Q by C, C1 V1 plus C2 V2 by C1 plus C2. This is the expression for the common potential. Now after the redistribution of charges, suppose charge on the conductor 1 is Q1 dash, that is C1V, because V is same for both. Q2 dash is C2V, and if you take the ratio Q1 dash by Q2 dash, that is equal to C1 by C2. That means the charge stored in the capacitor is, or the conductor is proportional to its capacitance. Q is proportional to C, as you know before also. That means Q1 dash by Q2 dash is C1 by C2. Now let us find what is the loss of energy due to redistribution of charges. You know, when two conductors are connected and charges are redistributed, and you will see now there is always loss of energy due to redistribution of charges. Now we will take two conductors having charges Q1 and Q2, potential V1 and V2, capacitance C1 and C2. When they are connected, the expression for common potential is V is equal to C1 V1 plus C2 V2 by C1 plus C2. Then what is the initial energy stored? Initial energy before redistribution, for first one it is half C1 V1 square, for second conductor half C2 V2 square. Then what is the final energy? The final energy when they are after redistribution, when charges are redistributed, they will get a common potential. V is constant for both. So for first one half C1 V square, for second one half C2 V square. So V square can be taken common. So half C1 plus C2 into V square. Now the value of V is C1 V1 plus C2 V2 by C1 plus C2. Just put the value, and so UF is equal to C1 V1 plus C2 V2 whole square by 2 C1 plus C2. This is the final energy. This is the initial energy. Then let us find the difference between initial energy and final energy. Initial energy is half C1 V1 square plus half C2 V2 square. Final energy is C1 V1 plus C2 V2 whole square by 2 C1 plus C2. So Uy minus Uf, initial energy minus final potential energy, that is equal to, after simplification you will get C1 C2 into V1 minus V2 whole square by 2 C1 plus C2, which is always positive. That means Ui is greater than Uf. Initial energy is always greater than final energy, because the difference is always a positive quantity. It is a square, whether V1 is greater than V2 or V1 is less than V2, so it is a positive quantity. So it is very clear that there is always loss of energy due to redistribution of charges. Now, when two conductors are connected having a potential difference, so there is a flow of charge from higher potential to lower potential through the conducting wire. As the charges are flowing in the conducting wire, some energy is lost in the form of heat. That's why there is always loss of energy due to redistribution of charges.